Okay, physics students. Today I'm going to be going over the concaves. All right, so today we're going to just go through the study guide here. We'll start with the problems. And first one is a concave spherical mirror has a radius of curvature of 7 centimeters. If a 3 centimeter object is placed 18 centimeters from the mirror, what is the image distance and the height of the image? Draw a ray diagram of this. So I'm not going to draw this perfectly to scale, but I am going to use a straight edge here. And so usually I start out with my axis, and then I'll just draw a mirror on. Now, obviously, it's not concave or convex. It's just a line, but it still represents my mirror. And the radius of curvature is 7 centimeters. So I'm just going to pick a place, and I'm going to call that 7. All right, now, that is my C position, the center of curvature. And I know that knowing that gives me the focal point. The focal point is 3.5 centimeters. So that's where I put F. And then it says that the object is 18 centimeters away from the mirror. Well, if this is 7, then that would be about 14, and that's going to be about 18 right here. So this is going to be P. This is my object distance. And it says that it's 3 centimeters high. Okay, so again, none of these are really to scale, but again, it gives you the idea, and it's going to be somewhere in the ballpark. All right, so then there are 3 different possible rays that I can draw. I can draw my first one goes parallel from the object to the mirror, and then that will reflect back through the focal point. All right, then our next one is we go from our object through our focal point. And then that reflects back parallel to the axis. Again, I'm not doing a great job here, but so this is ray number 1. This is ray number 2. The third possibility is to draw one that just goes from the object through the center of curvature. All right, so, okay, and again, that should intersect right here. Now, you only have to draw 2 of those 3 rays. You don't have to draw all 3 just to find that intersection point. And that's a little bit past the focal point. Let's call it, I don't know, let's say that Q in this case is 4. Okay, just guessing. And it's smaller and it's upside down. It's a real image. Okay, now the next thing you're supposed to do is solve this mathematically. So we have to use 2 equations. We have our mirror equation, which is 1 over P plus 1 over Q equals 1 over F. And we also have our magnification equation, M equals negative Q over P. All right, and so I don't enter anything into my calculator this way. This is how I would write it. P to the minus 1 plus Q to the minus 1 equals F to the minus 1. Because I've got that neat little X to the minus 1 button right there. That's pretty easy to use. All right, so I know P, I know F, and so I'm just going to rearrange. I'm going to bring P over to this side of the equation, and that's going to then be Q to the minus 1 equals F to the minus 1 minus P to the minus 1. All right, now that will solve for Q to the minus 1, but I don't want that. So really what I want to do is I want to take the inverse of both sides, inverse of this side, inverse of this side, and Q to the minus 1 to the minus 1 is just Q to the 1, which is just Q. All right, and then here we've got F to the minus 1 minus P to the minus 1, all to the minus 1. And now I can plug my numbers in. F was 3.5 to the minus 1, minus 18 to the minus 1, all to the minus 1. And now we get the calculator out. So I go 3.5, hit x to the minus 1, minus 18, hit x to the minus 1, equals And again, that's not my answer. I have to hit x to the minus 1 again to flip that up, and that is 4.34. So Q equals 4.34 centimeters. All right, now the second question is, how do you find the height? Now, one additional thing on the equation here, height is also h prime over h, and this is the h prime is the image height, and h is the height of the actual object. All right, which we said was 3. Okay, now I don't know what the magnification is, but I do know Q, I do know P, and I do know H. So I can solve for H prime. So let's do that. So negative Q over P equals H prime over H. And I'm going to multiply both sides by H. And so that's going to be negative QH over P equals H prime. And let's plug those numbers in. Negative Q is 4.34 centimeters times H, which was 3 centimeters. That was given in the problem. It's a 3 centimeter object, all over P, which is 18. And 2 of those centimeters will cancel out. And what I get here then is negative 4.34 times 3 divided by 18. And that's negative 0.72 centimeters. Okay, now what does that negative sign mean? It means that it's an inverted image, and therefore it's also real. So this is the height. All right, so that's number 1. Let's move on to number 2. Okay, number 2 says we have a mirror ball. It has a diameter of 10 centimeters and an object is placed 8 centimeters away from it. What is the magnification of the object and what is the location of the image? Draw a ray diagram of this. So when you think, what is it? You might be saying, what is a mirror ball? Well, it's a ball and it's made out of a mirror. All right, now this mirror ball, if I draw the whole thing, look like this. Okay, and it says that it has a diameter of 10 centimeters. All right, so the whole thing here is 10 centimeters. Well, what's half of that? That is 5 centimeters. Why is that important? It's important because that's the center of curvature of the outside of this. That's the mirror. Okay, we've got an object that's 8 centimeters away from it. This is 8. Oh, P equals 8. Right. So this is a convex mirror. Okay, because it's bending away from the object. This is the center of curvature. This is actually negative 5. The focal point will be half of that, which is negative 2.5. Okay, and so negative 2.5 is on the back side of the mirror. No rays of light are actually going to penetrate through this mirror. They're going to all bounce off, but we're going to treat it as if they do. And so we start out with our first ray, and that will go parallel to the mirror, just like before. This is ray number 1. And then it's going to bounce off as if it's bouncing, if that ray of light is coming from the focal point. And I'm going to draw a dotted line behind the mirror to indicate that. Okay, so this is ray number 1. The second ray that I draw is going to go, we're going to draw it as if it's going to go straight to the focal point. But again, it's blocked by the mirror, and that's going to bounce off parallel. So this is ray number 2. Okay, now I'm going to dot that line backwards as if that's where it's coming from. And again, where those 2 rays cross, that's where my image is going to be. Now that second ray is kind of more complicated. what I would do is I would just go to the one that goes right through the center of curvature, because again, I don't have to do anything fancy here. I can just draw a ray of light that's going to hit the mirror and bounce directly back on itself. But when I draw that, again, I dot that line back through there, and it still ends up at the same place. This is my Q. And again, that Q value looks like it's going to be something just shy of 2. Okay, so we can check that with the math. So we'll go back to that same equation that we were using before. P to the minus 1 plus Q to the minus 1 equals F to the minus 1. Same mathematical process. Bring the P over to this side. So it's going to be Q to the minus 1 equals F to the minus 1 minus P to the minus 1. Take the inverse of both sides, and then plug in our numbers. So that's going to be negative 2.5 for the focal length to the minus 1 minus our image distance. And again, that's always positive because it's a real thing that exists in the real world. Take that to the minus 1 and then the rest here. So let's plug in those numbers. Negative 2.5 to the minus 1 minus 8 to the minus 1 equals, and then that's all to the minus 1 power, and that's negative 1.9. And that makes sense, okay, because it should be negative because it's on the back side of the mirror. All right, then to find the magnification, M equals negative Q over P, right? Q, we just said, was negative 1.9, so it's negative 1.9 over P, which is 8. Well, negative is positive, so it's just going to be 1.9 divided by 8. And that's 0.237, so we'll just say 0.24. Now notice there are no units for magnification, it's just a ratio, and so what this is saying is that it's 1/4 the height of the original image, and I don't know, looks about right. Like I said, I didn't draw this exactly to scale, but it is upright, meaning that the magnification is positive, and it's smaller. And it looks like it's about 1/4 the size. Okay, let's move on to number 3. Number 3. A concave mirror has a radius of curvature of 60 centimeters. A 5 centimeter tall object is placed 15 centimeters away from the mirror. What is the image location and the magnification of the object? Draw a ray diagram of this. All right. So once again, I'm going to draw my axis and my mirror. And it says that it has a radius of curvature of 60 centimeters. Okay, so we're going to call this 60 centimeters here, and this is our C, which means that our focal point is about halfway. Again, this is a concave, so everything's going to be on the front side. At least, I shouldn't say that. Focal point is on the front side. The object is on the front side. Now the object is 5 centimeters tall, and it's 15 centimeters away from the mirror. So it's actually inside the focal point, and it's about this tall. Okay, so Q equals 15 centimeters. All right, so now, once again, I need to draw my rays. So ray number 1, again, always starts out going parallel and then back through the focus. All right, but all reflected rays we dot back as if they are coming from the back side of the mirror. All right, so that's ray number 1. Okay, and then ray number 2 goes from the focal point through the top of the object to the mirror, and that is going to bounce back parallel. Try to get this as close as I can. And then I'm going to dot that reflected ray back as well. And then the last one is the one, again, where I just go to the center of curvature. And I'm going to connect that through the top of my object. That's going to reflect back this way, but I'm going to dot that reflected ray back. And once again, you can see all three of these lines are all intersecting back here. And this is my image. Now notice the image is on the back side of the mirror, meaning that that is going to be a virtual image. And it's upright, so we know that it's virtual anyway. So then the question says, what is the image location and magnification of this object? So I will, a sheet of paper here. So that's going to be, once again, p to the minus 1 plus q to the minus 1 equals f to the minus 1. And I'm not going to go through the math on this again. If you want to see that, go back to one of the previous problems. But this is going to be q to the minus 1 equals f to the minus 1 minus p to the minus 1 all to the minus 1. This goes away because I'm inversing both sides. And so this will be then 15 to the minus 1 minus, I'm sorry, 30, f is 30. 30 to the minus 1 minus 15 to the minus 1. And that's negative 30. Okay. And that makes sense. Look at that. This is 30. That's about 30 right there. The negative sign indicates that this is a virtual image because it's on the back side. Magnification, m equals negative q over p, negative 30 over 15, and that's a positive 2. Is that image twice as tall as this one? Looks about that. So again, that's what you need to do for your test. You only need to do 2 of those 3 rays that I drew, though. Usually the center of curvature one, the one I do third, is probably your best go-to for number 1. But then number 1 would be probably my second one. Number 2 you can do, but it's not the easiest. All right, let's move on to number 4. What is the frequency of blue light? The wavelength is 475 nanometers. Okay, so this is going to use our wave equation for electromagnetic waves, just like the regular wave equation, except this is c. We know that c, the speed of light, is 3 times 10 to the 8th meters per second. In this case, it's giving us a wavelength, lambda, of 475 nanometers. Okay, 475 nanometers is the same as 475 times 10 to the minus 9th meters. And that's what I need to use. So this equation, solving for the frequency, becomes F equals C over lambda. And that's going to be 3 times 10 to the 8th over 475 times 10 to the minus 9th meters. So 3 divided by 475. And that's 6.3 times 10 to the 14th. And that's going to be measured in hertz. All right, number 5. What is the wavelength of an electromagnetic wave? Oh, let me pull this down. Okay, what is the wavelength of an electromagnetic wave that has a frequency of 5.4 times 10 to the 12th hertz? All right, so again, we're going to use our wave equation, C equals F lambda. And now we're looking for the wavelength. So that equation will become lambda equals C over F. C, once again, is 3 times 10 to the 8th meters per second. That is always the case. And then F, in this case, is 5.4 times 10 to the 12th hertz. All right, and so I substitute my numbers in. Three to the 8th divided by 5.4, and you get 0.0000555. All right, so that's the tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths. So this is going to be 5.55 times 10 to the minus, what is that, fifth? 1, 2, 3, 4, 5. And that's going to be meters. All right, that does it for the math portion. As far as the rest of this goes, let's talk about those. Number 6, if two polarizing filters are overlapped at right angles to one another, what happens? So if you watch the notes, basically you have light. Okay, light comes at us in all different directions. Okay, up, down, left, right, every degree. A polarizer is kind of like a picket fence. So if this light is coming this direction in all the different orientations of it, everything that comes through the filter will be, the only things that can get through are the vertically polarized packets of light, right? Now, if you take another polarizing filter oriented at 90 degrees, that light, that vertically polarized light will not get through here and you will get no transmission. So if you have two polarizing filters overlapped at right angles to one another, there is no transmission. All right, so number 7, if polarized light has a horizontal transmission axis, only horizontal waves, how should a polarizing filter be oriented to block the light? So this basically, if I have horizontal waves of light coming at me like this, whoops, sorry, like this, I'm going to want to get a vertical polarizer to block that. All right, so it should be, if I have horizontal light, if I want to block it, I need a vertical polarizer. All right, number 8, what happens to the amount of light transmitted as the angle between the transmission axis of light and an electromagnetic wave increases? What happens to the amount of light transmitted? Now, this question is kind of, I think it means the angle between the transmission axis of light and polarizing filter. So as the angle approaches 90 degrees, light decreases. All right, move this up. All right, number 9, what are the primary subtractive colors? Primary subtractive colors are the ones that you're used to from, say, art class or kindergarten. Okay, you've got red, blue, and yellow. Those are the primary, oh, I'm sorry, that's incorrect. Let's try that again. Primary subtractives are magenta, cyan, and yellow. Those are the primary subtractives. When you mix them all together, you get black. Between magenta and yellow, you have red. Between yellow and cyan, you have green. And between cyan and magenta, you have blue. All right, these are the secondaries. Now, the next question is, what are the primary additive colors? So we basically, all the secondaries become primaries and the primaries become secondaries. So let's draw that. So I've got blue, red, and green. Okay, between blue and red, we have magenta. Between green and blue, we have cyan. And between red and green, we have yellow. Right? And in between, or where they all mix together, we get white. All right, so then number 11, what color does a red light and a blue light make? So then we come to the additives. Red and blue will make magenta. All right, number 12 takes us through what happens to the images that we make with a concave mirror as we bring the object closer and closer to the mirror, closer and closer to the focal point and even to the focal point and even inside the focal point. So if it's placed way out there beyond the center of curvature, we're going to have a smaller image. Okay, so here's my, say this is focal point, center of curvature, come out here and then there. I'm going to have a smaller real inverted image. Okay, so smaller real inverted. Now it's kind of redundant to say that it's real and inverted because all real images are inverted. Now if I put it right at the center of curvature, let's say this is C. Okay, here's my focal point. Now I can't really use the center of curvature one, but I can go from here to there. I can go from here to there, and they should intersect right where the center of curvature is. So this is going to be same size, real, and inverted. All right, now if I bring it in between the center of curvature and the focal point, okay, now the image is going to form out beyond the center of curvature, and it's larger. So now it's going to be larger, real, and inverted again. If I place it at the focal point, so here's my focal point, here's my object. This is going to go like that. Center of curvature is here. They connect. I've got parallel lines. You know the joke about parallel lines? They have so much in common, but it's a shame they'll never meet. Yeah, there is no image. And then for the last one, it says, what if you put it inside the focal point? Okay, so here's my focal point. Here's my object. That's a really bad drawing, but it's good enough. So this will connect, come off here, and then center of curvature. Here I've got a larger virtual upright image. And again, that's redundant because all virtual images are upright. It's on the back side. So think about what the trend is. As my object starts out here, I start with small objects that are close to the mirror. As it moves this direction, the object or the images start moving away and they start getting bigger and bigger. Okay, in fact, to the point where they get so far away, they go to infinity, and then they end up in the virtual realm, being much larger out here. You can go to the lab that we did with concave mirrors, and you can just, you know, start with your object way out here, and then move it in and watch what happens to that image as you go. All right, 13. How are the focal point and center of curvature related in a spherical mirror? The focal point is half the distance of the center of curvature. Number 14. How far away does the image in a flat mirror appear to be from the object that is reflected? It appears to be just as far, or from the object, it would be twice as far as you are from the mirror. So what does that mean? Here's my flat mirror. Okay. I have an object here that's 2 meters away. The image is going to appear to be 2 meters away from the mirror as well. From the object, that's 4 meters. Okay. So when I look at if I'm standing 1 meter away from a mirror, my image appears to be 2 meters away from me. All right, number 16, how are the angles, I'm sorry, 15, what kind of images do flat mirrors make? Flat mirrors make virtual, same size images. All right, number 16, how are the angles of incidence and refraction related? They are equal. 17, what's the difference between specular and diffuse reflection? Specular, you can see actual images. Diffuse reflection typically come from rough surfaces. And all you can see is blobs of light. You can't see like your face or whatever it is that's reflecting. Specular, you have shiny, orderly rays. 18, what happens to light intensity as you double your distance from a light source? The light intensity decreases to 1/4. This again is an inverse square law. So if I triple my distance, my intensity goes down to 1/9. If I quadruple my distance, my intensity goes down to 1/16. If I cut my distance in half, I now have 4 times as intensive light. Number 19, why is it that you can determine the frequency of any form of electromagnetic wave if you know the wavelength? It's because they all have the same speed. And that speed is c, and that is 3 times 10 to the 8th meters per second. Number 20, how do the speeds of different forms of electromagnetic radiation compare? They're all the same. 21, what region in the electromagnetic spectrum do we use when we see things? We are using the visible light portion of the spectrum. Again, it's a very, very tiny portion of all the light that exists. And then 22, what region of the electromagnetic spectrum is used for television transmissions? And that basically is TV transmissions are a form of radio waves. Okay, that is all I've got. If you have any questions, go ahead and send me an email. Otherwise, we'll see you for the test tomorrow.